It is section 4.4, Romberg integration. Romberg integration is to generate high accuracy results using multiple trapezoid quadratures obtained on refined partitions. In the previous section, we have analyzed that the composite trapezoid rule has a truncation error of order h squared over n equal subintervals of AB. This partition, we define T of n to be the trapezoid quadrature given in this equation. We'll begin the section with an effective computation technique for T of 2n as a refinement of T of n. Let's see this example. What is the explicit formula for T1, T2, T4, T8 in the case in which the interval is 0 to 1? By using this formula, T1, that's the case, we consider the interval as one subinterval. Now, T2, that is now with two subintervals, we can get that. Here, the pattern is from edge points, we have half contribution. From interior points, we have one contribution, and this value is h at the moment. Okay. Here, if you see here, now red colored input, the evaluation is given. That is a kind of extra. Already we have evaluation here, and this is an additional evaluation. Now, once we make this evaluation, then in next level, these three are the same from the early one, and then these two are extra evaluations. And what is the same from T4, we make a T8, and now these black inputs are already made from here, and these are new extra evaluations. Okay, that is the observation. From this observation, it is clear that if T of 2n is to be computed, then we can take advantage of the work already done in the computation of Tn. And for example, here we explicitly write the formulas. Okay, T2 is now same as this value, but rather than 1, we are using half, so that half of T1 plus now half of this value, that is exactly this one. Now for T4, here, this is, rather than half, we have a quarter, so that for these black inputs, now half of, that will be half of T2, and we try to add this extra contribution along with h value, that's quarter. So we have here now half of T2 plus a quarter of this extra contribution. And T8 is half of T4 and the h times and extra evaluations here. So in general, we can write down this one into this formula. T at 2n is same as half of Tn plus the grid size, so that is now current the subinterval size, and then here intermediate evaluations. So they are added to the half of Tn. Then we can get here T of 2n. Okay, that is the recursive trapezoid rule. We summarize that here. Now, if we try to refine by here twice more points in each level, each next level, we try to get here twice more points, then rather than n, we may try to use here 2i, 2 to the I, t, 2 to the I is same as half the previous one. Now, plus hi, hi is current the subinterval length, and then here extra evaluations and summed. Okay, that's the recursive trapezoid rule. So by using already evaluated without duplicated evaluation, we can get the trapezoid rule in various levels more effectively. Okay, now we'll go to the Romberg algorithm. By using the Taylor series method, we can prove that if f is smooth enough, then the composite trapezoid rule can be written with an error term in this form. Integral a to b f of x is now Tn. So that is along with n subinterval, and we get it. Of course, n equal subintervals, and Tn, that is trapezoid quadrature, and error can be written in this way. Rather than one term for the h squared, we can expand in this way. That is k2h squared plus k4h4 and so on. Now here ki are constants, independence of h. Now if we try to use twice more subintervals, so that t2n, then h will be halved, so that rather than h, we are putting half h, then we can get that one. As for Richardson extrapolation, we try to multiply 4 for this equation and subtract this one, and then divide by 3, then we can get here this formula, and along with the error, the leading order term is now fourth order. So that is the major idea of Romberg algorithm, and we can use this Romberg algorithm recursively as for Richardson extrapolation. So here we have Romberg algorithm. The complete algorithm of Romberg integration is formulated as, number one, we need the computation of the zeros column in the R matrix. And in the beginning, and we use one subinterval, and then two subintervals, and four subintervals, and 8 subintervals, and so on, so that we try to fill out the zeros column of R matrix. So each quantity in this column is trapezoid quadrature, but as going down, the values are refined one, so that more accurate. Okay, so by using this recursive trapezoid formula, you can get the values. And now we start working on extrapolation. Here I is outer the loop and J is inner loop, so that that is now here row-wise implementation. This scheme is exactly same as for Richardson extrapolation, but rather than the differentiation, and we are trying to get integrals, but the manner is exactly same because we start with that equation. We can eliminate this term by using this extrapolation, and if we use one more time of the extrapolation, then we can eliminate this term to become the scheme, for the scheme to become sixth order, and so on. Okay, so here we have example. Use the composite trapezoid rule to find approximations to here the integral from 0 to pi sine x dx. The true value is 2 by using here n is 1, 2 for a. Then perform so that the composite trapezoid rule will occupy the zeroth column of R metric and perform Romberg extrapolation on these results. Okay, here. Now, a is 0, b is pi, and function is sine x. Now, n is, now later we'll use this one, now I, so that I is moving from 1 to here 3, so that here the 2 to the I will be made. So the number of interval will be 2 to the I, so that when it is 1, this 2 subinterval. When it is 2, then 4 subinterval. When I is 3, then there will be 8 subintervals. Okay. Here we open array R metric, and then here in the beginning R00 will be gotten by using the one subinterval quadrature formula. Then output is 0, and by using the recursive trapezoid rule, we can get the below values. And then here now we do Richardson extrapolation here now, row-wise implementation. Okay, let's see the output. Here this is the output. And now true value is 2, and in the beginning it's 0, and now this value, and here when we are using 8 subinterval, we reach here about 1.97. 4 times this value minus this one divided 3 will make that. 4 times this one minus this one divided 3 is this one. And 4 times this one minus this value divided by 3 is that one. Now here 16 times this one minus this one divided by 15, that is this one. 16 times this one minus this value divided by 15 is this value. Now here 64 times this value minus this one divided by 65 is that one. As you can see here, that this is 8th order accuracy, and the error is really small. If you want to achieve this accuracy by using only trapezoid rule, then you have to get about 500 subintervals. Yeah, it's about not 500. In fact, you have to have about 300 subintervals. And here error will be quarter below, and you can estimate the error go down. Then okay, it's about 500. Okay, if you choose about 500 subintervals, then you can recheck that accuracy. Now, by using this extrapolation, Romberg integration, we can get, even though we are using only 8 subintervals, we can get such a good approximation. Okay. Okay. The true value for the integral is true. Use the table in here, okay, to verify that the error is in order 4 for j equal 1 here. Now, for that one, the order 6. So you can measure quite easily. That is the 6th order convergence. And if you add one more, then again, you can check this as on 8th order convergence. You can do it. Okay. Okay, that's the end of the section. Thank you.